In this video, we're going to start talking about how we can talk about domain changes when we're reducing rational functions. Before, we have practiced with reducing rational functions in general, but the focus today is, in addition to simplifying the expression, we want to talk about how that affects a domain along the way. And before we even start, we can start talking about the domain restriction for a rational function. In general, just like anytime we have fraction, we want to make sure the denominator is not equal to 0. So if we look at the question in part A, we can see that we have a denominator of 8x squared. So to start with, we had 8x squared in the denominator, and we don't want that to be 0. So if we want to talk about the domain restriction at this point, we just want to solve this inequality. And here we can divide 8 on both sides and get x squared doesn't equal to 0 or x doesn't equal to 0 is the original domain to start with over here. And as we go along the way, we want to kind of make note of any cancellation, any simplification we do, and see how that affects the domain restrictions we have. And now to simplify it, we can see on the numerator we have a higher degree polynomial, and for that type of problem we want to think about factoring, and the first thing we want to do for factoring is to check GCF. Here the GCF would be 2x because all the coefficients are even and they all contain x, and the lowest degree of x is x to the first degree. So if we factor that out, we are left with x squared plus 5x minus 11 over here. And once we have this left, we have this all over 8x squared. And now at this point we can see that 2x and 8x squared have a cancellation that we can go through. And 2 and 8 have a factor of 2, so that 8 turns into a 4. And also we have a factor of x that we can cancel out over here. And when we are canceling out a common factor, we are essentially dividing that factor on both sides of the fraction or the rational function. And by doing this division, we are assuming whatever we're canceling out is not equal to 0. So we are making this implicit assumption that x doesn't equal to 0, which does match our condition that we start with over here. But just as a habit, I'm going to note that x doesn't equal to 0 is the assumption we made. It is satisfied by our original domain anyways, which is great because that means our domain hasn't changed. We're sticking to the same restrictions. And then if we look at what's left over at this point, we are down to, on the top, just x squared plus 5x minus 11, and this is all over 4x. And if we check on the numerator, we could try to see whether we can factor it again, and if you check it, you will see we want to find two numbers. The product will be negative 11 and the sum will be positive 5. And pretty quickly, I hope you can rule out that these two numbers won't be integer values, because the only factors of 11 would be 11 and 1, and no matter how we do the combination, we can't get a sum of positive 5. So that means we can't factor this numerator any further, and that's as far as we can do over here in general in terms of the domain in terms of the simplification. So we would just stop here and say that's as far as we would go in terms of simplifying. And we notice that overall the domain at the end is still going to be x such that x doesn't equal to 0. It stays the same over here. You can also use the interval notation, which would be negative infinity to 0 union 0 to infinity. So we can see this domain didn't change from before. And you can make a note of this as well. Now moving on to part B, we can do the same thing and start off by looking at the initial denominator. And to start with, we had z squared minus 25 equal to 0. You can use either the square root property or the factoring then zero product principle. So if you do the factoring, you would want to use the difference of squares factoring, which turns into z plus 5, z minus 5, because 25 is a square number. and that's equal to 0, and we get z doesn't equal to positive or negative 5 in this case, and that's the original domain restriction we had. And now moving on to simplifying, we can see on the bottom we already factored to be z plus 5, z minus 5. This is also part of the reason why I chose to use a factoring process, because we have to do it in the denominator anyways. And now on top, if you didn't recognize it, you could try to do the factoring and find two numbers that multiply to be 5 and add up to be negative 10. But if you recognize the special form, this is actually a perfect square form, because if we do half of 10, that squared gives us 25. So on the top we actually just have z minus 5 squared. And again, you can get the same result just by thinking what two numbers would multiply to 25. You'll turn out to find negative 5 and negative 5. You'll notice they are the same factor as well. And in this process, once we do this, we can see on top and bottom we both have a factor of z minus 5. So I'm going to go ahead and cancel them out. Once I do so, I'm left with z minus 5 on top and z plus 5 on the bottom. And as I do this simplification, I'm making this assumption that whatever I cancel out is not equal to 0. So what I canceled out was z minus 5, and that concludes that z doesn't equal to 5. Again, it matches our domain restriction already over here. So now if we look down to our final result, we can actually see that in our final form we can't simplify this any further, and we would just get a denominator of z plus 5. Therefore, if we look at it, we want to make sure that the denominator, z plus 5, doesn't equal to 0, and therefore z doesn't equal to negative 5 in this case. And therefore, if we only look at the final form, we can state for this final expression, the domain is going to be x such that x doesn't equal to negative 5. And that will be the only restriction we have in the final form. And you can see this is different from what I started with when we first talked about the domain. Here, the domain is going to be actually z, not x, right? Z such that z doesn't equal to plus or minus 5 in this case. So we notice that there is indeed a domain change, whether you are simplifying, you're looking at the simplified form versus the original form. So we would say these two expressions are equal as long as z doesn't equal to our value of positive negative 5 in this case. And compared to what happened in part A, we noticed that the original domain was the same as the simplified form. So the original expression is exactly equivalent to the final form on the entire domain, because we have x doesn't equal to 0 as the restriction the entire time. And now moving on to part C, we have again the denominator 3t minus 5 to start with. So 3t minus 5 doesn't equal to 0 will be our restriction, and you will get t doesn't equal to 5 over 3 as our original domain over here. And now moving on to simplifying it, we can't do much with the denominator, but on the top we can check whether we can factor that. And on top, if we want to factor, we would have to use the AC method. That means we want the product to be a times c, which is 6 times negative 5, or negative 30, and we want the sum to be negative 7 over here. And we can think about the two numbers that would work. In this case, I believe the two numbers are negative 10 and positive 3. So we can go ahead and use these two coefficients to rewrite the middle term. That becomes 6t squared plus 3t minus 10t minus 5 over here. And let's group the first two terms together, last two terms together, connected by addition. And then from here we can go ahead and say that if we want to factor by grouping, the first group has 3t in common, leaving us with 2t plus 1. The second group has negative 5 in common, leaving us with 2t plus 1 again. And this is all over 3t minus 5. And if we go ahead and factor the top further, we would get 3t minus 5 times 2t plus 1. And this is all over 3t minus 5. And then if we go through the cancellation, we have 3t minus 5 cancel each other out. Again, that brings in the domain restriction that we technically had already, that 3t minus 5 doesn't equal to 0, or t doesn't equal to 5 over 3 in this case. So in this case, if we have the result, we would just get 2t plus 1. And now if we look at this domain down at the bottom, we see the domain is actually all real numbers. We can go anywhere from negative infinity to positive infinity, and that domain changed from the original expression to the final expression. So these two expressions are equal to each other except when t is equal to 5/3. Now moving on to part D, we have 3x minus 5 squared in the denominator. So the original domain comes from 3x minus 5 squared doesn't equal to 0. We can use a square root property right away and get us 3x minus 5 doesn't equal to 0, and get the result that x doesn't equal to 5/3. And that's the original domain that we have for the function. And as we go on, we want to check whether there's anything else we need to include in terms of the consideration. So on top we have a perfect a difference of squares again, because 9x squared is a perfect square. It turns out to be 3x entirely squared, and then 25 is 5 squared. So we can use a difference of squares to get 3x plus 5, 3x minus 5, all over 3x minus 5 squared. And as a result, we can cancel out a factor of 3x minus 5, and leaving us with 3x plus 5 over 3x minus 5. So along the way, as we're canceling things out, we are making the assumption that 3x minus 5 doesn't equal to 0, because that's what we had to cancel out over here. And again, we already had that restriction to start with. And now if we look at the final result, we still have the same denominator. The denominator stayed the same as 3x minus 5. So for the domain restriction, we're going to have exactly the same as what we started with. We want x such that x doesn't equal to 5/3 over here. So in this case, even though we had some cancellation, the domain stayed the same over here. And that's how we can look at the domain restrictions when we're simplifying these rational functions.